It was first indicated that invisible light existed in 1800 by astronomer Sir William Herschel, who examined the temperature of different shades of light shone out of a prism. Seemingly out of curiosity, he placed a thermometer beyond the field of red light. Finding that this thermometer was indeed the hottest, he discovered infrared light. Inspired by this feat, a surge of scientific inquiry throughout the 1800s uncovered ultraviolet light, radio waves, and even X-rays in 1895 by Röntgen. It was only in the early 1900s that these high-energy waves were indeed confirmed as variants of light. To fully grasp electromagnetism, we need to step back to 1882, when Heathersdale compiled the research of James C. Maxwell into the four Maxwell equations we know today. This third equation, the integrated Maxwell-Faraday equation, is most essential to identifying the interrelation of electric and magnetic field. On the left we have E, the electric vector field, and on the right B, the magnetic vector field, measuring the strength of such fields in different points in space. Then we have DL, infinitesimal vectors that line the perimeter of a current carrying circuit, with their product quantifying the degree by which the direction of the electric field and these DL vectors align. And since these DL vectors are infinitesimally small, this whole side of the equation identifies the behavior of electric fields on the circuit. Then we have DS, a vector representing the infinitesimal area within the space of this looped circuit. Again, the product of this with B indicates the magnetic field's influence over the circuit's area, accounting for vector strength variability in different points in space. Evidently, this indicates the negative rate at which the magnetic field's influence on the circuit changes. And after all this, we have a looped electrical circuit with a magnetic field flowing through it. You know what this is, it's electromagnetic induction! Well done. And we shouldn't look at this as some overglorified version of electromagnetic induction, but rather a code by which everything we may want to account for with electric and magnetic fields is accounted for. Principally, moving electric fields generate magnetic fields and vice versa. And with this phenomena rose electromagnetic radiation, waves that propagate upon both electric and magnetic fields as photons, emitted when charged particles decrease in velocity upon opposing an electric field's direction. The quantity of energy packaged within each photon is indicated by the vibration of the electromagnetic field on which it's going through, or its electromagnetic frequency. Each form of radiation bears a different energy or frequency range, and it's by this factor that the electromagnetic spectrum is ordered. All radiation forms exert energy into a substance's atom. These atoms as electrons vibrate upon energy absorption, which due to their motion generates electromagnetic waves of identical frequency to the initial wave into other electrons and throughout the substance. The most powerful form of radiation we experience daily is light, with this amount of energy. But it's when radiation bears enough energy to ionize, which is that energy by the way, that we start to worry what's been touching us. To ionize is to transfer enough energy into the electrons of an atom to drive it out into independence, which in living tissue changes a cell's chemical properties, enabling DNA breakage to induce cell death or mutation. Cell death is predominantly observed in sunburns, where UV radiation severs cell DNA to inhibit mitosis and prolong the presence of dead skin cells as burn. However, if cell DNA is impaired but continues to undergo mitosis, mutated cells such as cancer cultivate. The dire ionization symptoms predominantly derive from gamma rays, the radiation with the highest form of energy on the spectrum, and it's emitted as excess energy when nuclei stabilize from an excited state. The extent of our contemporary understanding of electromagnetism and the technology we employ to measure such phenomena is restricted to the spectrum, when in reality the range of wavelengths could be infinite. It's considered that once wavelengths diminish beyond attometers, the electromagnetic field incorporates the field of weak nuclear forces, entering a whole new playing field, a 1,000th the size of a nucleon. Due to its complex nature, going this deep into electromagnetism wouldn't just require like an extension to this spectrum, but a whole different spectrum entirely, because there are additional implications to wave propagation amongst forces capable of changing a particle's charge. That would be crazy to study. No such observational evidence has been discovered, which you could argue is purely due to the restriction of contemporary technology. Because think about it, right? You have radios which only detect radio waves, and you have your eyes which only detect light. So what means of technology is needed in order to detect new additions to the spectrum? Well, who knows?